So let's apply these photochemical concepts, the concept of photochemical reactions, to the molecule of ozone. Solar energy drives the formation of ozone. A molecule of oxygen in an excited state is able, it can absorb more solar radiation in the UV spectrum of a particular wavelength to generate 2 atoms of oxygen. And 2 atoms of oxygen can react with more molecules of oxygen to create the molecules of ozone. And that is the overall reaction. The overall reaction can be simplified as 3 molecules of oxygen of O2 make 2 molecules of ozone. But the intermediate steps are the interesting ones: the formation of this atomic oxygen and the reaction of the atomic oxygen, the atom of oxygen, with the molecule of oxygen, O2. Ozone absorbs solar energy to form, and it also absorbs solar energy and dissociates. So a molecule of ozone can absorb solar energy of the right wavelength. It's in the UV part of the spectrum, ultraviolet part of the spectrum, and will dissociate to form a molecule of oxygen, O2, and liberate an atom. And this is a very unstable species, and they will react with another molecule of ozone to make the stable species of oxygen, which is the molecule of O2. So it's these characteristics, this fact that it absorbs solar energy when it dissociates, that is what protects the Earth, the surface of the Earth, from high energy solar radiation, from the UV ultraviolet part of the spectrum of the solar radiation, because those wavelengths mean that all the UVC lights, UVC rays are absorbed, and almost all, around 95% of all the UVB rays are absorbed, or UVB light is absorbed, and a certain amount of UVA is absorbed and is the one that actually gets, reaches the surface of the Earth. The previous process I showed was what happens when ozone reacts oxygen reacts to produce ozone, and then ozone reacts to liberate oxygen, and it's absorbing that UV light to do that process. There are atoms that can accelerate or the destruction of ozone, the reactions that involve breaking down oxygen. Breaking down ozone, and we call that catalysts. Well, we call that catalysts. They are catalytic species. They don't get destroyed in the process. They continue destroying more molecules of ozone. The general mechanism for all of them is the same. You've got your molecule of ozone that can react with your ozone destructing species that I've called X to form this intermediate compound and liberate some oxygen. And then the intermediate compound, the oxide of that species, can react with another atom of oxygen to form more oxygen. So the overall reaction is that ozone gets destroyed and more diatomic oxygen is formed. So that adds to the natural destruction of ozone by absorbing UV light. So on one hand, you have a certain amount of ozone being created and a certain amount of ozone being destroyed by different wavelengths of solar radiation, and that there is a balance to it, an equilibrium is reached. In the moment you add other species that can aid to the breaking of ozone, you have more reactions breaking down ozone than reactions forming ozone, and that is the problem. That's how ozone, the destruction of the ozone layer occurs. And you have all sorts of species that can help it can catalyze that process of destruction of ozone, several radicals. You have radicals derived from the hydroxyl ion, a hydrogen radical, a hydroxyl, or a peroxide. This is the name of this radical. You have radicals derived from nitrogen oxides, the nitrogen monoxide radical and the nitrogen dioxide radical, and you also have chlorinated radicals, and that comes from chlorofluorocarbons, CFCs, that I will cover in a future slide, that produce this chlorine radical and these chlorine oxide radicals. So all these species help the process of destruction of ozone in the ozone layer. So as an example, how does a nitrogen oxide catalyst act? Well, you can get these nitrogen oxide radicals from a couple of places. You can get them from nitrous oxide, and that's typically associated with agricultural processes, which are the ones that release nitrous oxide. And you can get it, you can also produce, get nitrogen oxide catalyst radicals from the combusting of fossil fuels. Combusting of fossil fuels, cars, or used for electricity and power generation, produces nitrogen monoxide that then evolves to form nitrogen dioxide, and then can evolve to form nitrogen oxide radicals. So for example, here there is an example of what would happen when nitrous oxide, N2O, reaches the stratosphere. With the right electromagnetic radiation, with the right wavelength, it splits into nitrogen and the oxygen atom, and then this oxygen atom gets activated and reacts with another molecule of nitrous oxide to produce the nitrogen oxide radical. And that is the one that participates in the destruction of ozone. In the case of the nitrogen oxides, the nitrogen oxide radical, it does not need any specific reaction to happen. It's simply with the right wavelength of solar radiation, the nitrogen oxide radical is formed. And what does it happen? That the nitrogen oxide radical reacts with a molecule of ozone to generate diatomic oxygen, O2, and then the product of that reaction, which is nitrogen dioxide, can react with an atom of oxygen and regenerate the nitrogen oxide radical and produce more oxygen. So the net process is that ozone gets destroyed and oxygen, O2, is formed. And as you can see, the key point is that this is a catalyst. It does not get destroyed in the process. A molecule of nitrogen oxide can destroy one molecule of ozone, get recovered, and then destroy another molecule of ozone, etc. in a more or less unlimited fashion, or at least it will take a long time for that nitrogen oxide to be depleted. Nitrous oxide measurements have increased over time from the 1800, 19th century towards the beginning of the 21st century. The concentration of nitrous oxide, N2O, has increased. Which that means that there is more nitrous oxide, so there is more in the atmosphere, there is more going into the stratosphere, and there is more to ozone destroying nitrogen oxide radicals in the atmosphere. It then can react with water vapor, with molecules of water in the air, to form nitric acid, which is that does not interfere with ozone. So we call an inert reservoir. So if the nitrogen monoxide becomes nitric acid, it will stops being involved in this ozone destruction cycle, it does have the problem that eventually if it falls down into the surface of the earth as rain, it can produce, it does cause problems with another pollution problem, which is acid deposition, acid rain.